So, we will continue our discussion on principle of hydraulic machines and system design. Today we will discuss about reaction turbine, that is we have discussed that the hydraulic turbine can be classified based on the utilization of head available. So, one is impulse turbine, Pelton wheel, that we have discussed. Today we will discuss about the radial flow reaction turbine, that is Francis turbine, and then we will discuss about the axial flow. So, today we will discuss about the operational principle of a Francis turbine, and then we will work out an example to see that how we can based on the available head, how we can get the total power and what should be the blade angle, all those things. So, to do that, let us I will first draw the schematic of a reaction turbine, and then we will discuss slowly about different features of the reaction turbine and how it is different from the impulse turbine. So, if I draw the schematic, so today we will discuss about reaction turbine. As I said that the reaction turbine is different from impulse turbine, since in a reaction turbine pressure changes gradually as the fluid flows through the runner. So, what in case of a impulse turbine, we have seen that only 1 and 2 buckets are involved at a time to get the conversion of the energy that is occurring. But in case of a reaction turbine, this energy conversion takes place gradually throughout the entire portion of the runner, and that is the basically fundamental difference between reaction and impulse turbine. So, today we have taken example of a radial flow, that is what I told you, radial flow reaction turbine. One example is the Francis turbine. So, if I draw the schematic, first let me draw the schematic of a reaction turbine. So, if I draw the schematic, so this is the schematic of a radial flow reaction turbine, is Francis turbine. This is, I am now giving the, I am just labeling different parts of it. This is draft tube, this portion is runner, this is known as scroll casing, this is shaft of the turbine, and these are known as guide vanes, or sometimes they are known as wicket gate. And if I draw the another view here, so this is the cross sectional view. So this is draft tube, this is runner, shaft, we have scroll casing, and then this is draft tube is very important part of, this is an integral part of the total hydroelectric power plant equipped with a radial flow, or I mean reaction turbine. But this draft tube was not there in case of a Pelton wheel, that is what we have seen. So if I draw the schematic of a hydraulic turbine again, then we have a few wicket gates. So we have a few wicket gates like this, and then there will be a scroll casing, so this is scroll casing, this is schematic. Here fluid is coming from penstock. So fluid is coming from penstock, these are called guide vanes, and this is of course runner, So we have drawn the schematic of a reaction turbine. We have given this cross sectional view as well as the schematic, I mean the how it looks like. Then we have labeled different parts. We have a scroll casing, shaft, of course shaft will be there. Another important component which is integral with this turbine is the draft tube. We will discuss one by one what is the function of that. Then we have guide vane. We also will discuss what is the function of the guide vane, and then scroll casing. Now as I said you that when we talk about reaction turbine, it differs from impulse turbine. So the principal distinguishing feature of a reaction turbine, how it is differ from impulse turbine, is that in case of a impulse turbine, entire head available, gross head rather head available at the inlet of the turbine is converted to the kinetic energy of rotation of the runner. Before it almost entire head is converted before it goes to the turbine inside the turbine. That is entire energy conversion taking place through the nozzle itself. Maybe 1 or 2 buckets at a time are engaged for this energy conversion through the nozzle. Now in case of a reaction turbine, only the part of the overall energy, so I am writing how it is differing from impulse turbine. So from the schematic again we need to look back the schematic, but how a reaction turbine is different from the impulse turbine. We will discuss one by one. So, as I said you that in a impulse turbine almost entire energy conversion takes place before fluid goes to the runner, and this energy conversion takes place through nozzle, and at a time maybe 1 or 2 buckets are involved. But in case of a reaction turbine, only a part of the energy conversion takes place before the I mean why? Because pressure head is converted to the velocity head, that is kinetic energy of the wheel, the runner. Now only part of the available head is converted to the velocity head before it goes to the runner. So first of all, in a reaction turbine, only part of the overall head is converted to the velocity head before the fluid is reached at the runner. So before fluid reaching at the runner, only a part of the overall head, that is pressure head, is converted to the velocity head, but this is not the true for an impulse turbine. This is not the case for the impulse turbine, because almost entire part of the velocity pressure head is converted to the velocity head through nozzle, and at a time maybe 1 or 2 buckets are involved for this, to obtain, rather to increase the kinetic energy of the wheel. Second is very important, that is what I am telling, that in case of a impulse turbine, at a time only 1 or 2 buckets are engaged for this. So instead of engaging only 1 or 2 buckets at a time, working fluid which is the case of a impulse turbine. Working fluid completely fills the runner, completely fills the passage, entire passage, completely fills the runner passage, So if I now go back to my previous slide, it is clear that when water is coming from penstock, it is going through the scroll casing. It is sometimes it is known as spiral shaped casing. This is spiral shaped casing. So this is spiral shaped casing. A special name is scroll casing, it is called. So whenever water is coming from penstock, it goes through this spiral shaped casing, but its name is scroll casing, and then the working fluid engaged almost all the blades, entire runner at a time, instead of engaging 1 or 2 buckets in case of impulse turbine. That means it is not the fact that only 1 or 2 bucket will be involved for this energy conversion and from there entire wheel will be rotating. It is not the case. Rather, whenever water is or working fluid is coming from penstock, it will go through scroll casing and it will completely fills the entire runner passage, and while it is completely filling the entire runner passage, there only the maximum energy conversion will take place, rather from overall head, that is pressure head, to the velocity head of kinetic energy, velocity head, and we will have some kinetic energy of rotation of the runner. So this is another important difference, and since it is very important, since the entire runner is engaged for this energy conversion in case of a reaction turbine, but while we have seen that only 1 or 2 buckets are involved for the energy conversion in case of impulse turbine. So if we would like to obtain a same power output from a hydroelectric power plant, so if the power plant is having a reaction turbine, then we require lesser, the wheel diameter will be less, wheel diameter and entire turbine size will be very less. So it is very important that instead of engaging only 1 or 2 buckets at a time, working fluid completely fills the runner and pressure changes gradually, pressure changes gradually as the working fluid passes through runner, right. This is important. Third is very important, since the entire circumference of the runner, rather of the reaction turbine is in operation, operation for developing power or generating power, since entire circumference of the turbine, of course reaction turbine we are talking about, is in operation for generating power, wheel diameter call it, or runner size is need not to be as large as that of impulse turbine. Since entire, as I said you, since entire circumference is in operation, that means the pressure changes gradually as it passes through the runner. So that means all the entire runner passes is in operation while this energy conversion taking place. That is why the rotor size or runner size should not be as big as that of impulse turbine for generating to obtain same power output. This is very important. So that means it is not the case like an impulse turbine, because in an impulse turbine only 1 or 2 buckets are involved at a time and energy conversion taking place from nozzle and is striking the buckets. So since only 1 or 2 buckets, so of course to obtain the higher, if you would like to obtain same power output from 2 different power plants, one is equipped with impulse turbine, another one is equipped with reaction turbine. And so of course in case of a reaction turbine, because of its operational feature, we need not be high, we need not to have a high wheel diameter or high runner size, which is there and which should be the case for the impulse turbine. So this is economic, this is good, that entire plant should not be as big as high in case of a impulse turbine. This is the fundamental difference between the reaction, how a reaction turbine is different from impulse turbine. So these are the different characteristics feature of a reaction turbine, and it makes it that these features make this turbine to be different from impulse turbine from constructional point of view as well as the operational point of view. Fine. Second thing, we have discussed here that the water is coming from penstock, and as water moves through the runner, through casing, spiral shape casing, sometimes it is known as scroll casing. So the casing is designed in such a way that we have seen that in case of a pump, when water is coming out from pump and we have a casing, also there is a spiral shape casing we have, but the area is gradually increasing, so that the velocity head can be converted to pressure head before it goes to the discharge point, because the entire purpose was in case of a pump is to develop a head. But in case of a turbine, whatever we are observing here, that the scroll casing or the spiral shape casing is designed in such a way that the velocity will remain almost constant as it passes through the casing. This is very important, that the fluid velocity will remain constant into the casing. So this is another important feature. Second thing, this entire casing which surrounds the runner. So I am writing here that what about the special feature of the spiral casing. So spiral shape casing, which is known as also scroll casing. So spiral shape casing or scroll casing, this is very important, that it should be designed in such a way the spiral shape casing or scroll casing should be designed in such a way that it will completely surround the runner. So, this casing completely surrounds the runner. The scroll casing completely surrounds the runner, this is very important, and the casing is designed in such a way that the fluid velocity will remain constant while flowing through the casing, So, these are the two important features. First one is the scroll casing completely surrounds the runner, of course we have seen from the schematic, and casing should be designed in such a way that the velocity of the working fluid, whatever is coming from penstock, the velocity of that fluid will remain almost constant while flowing through the casing. So, this is another important aspect for the casing shape. Now, if I go back to the schematic, so what is happening? So, fluid is coming from penstock, it is now entering to the casing, and while it is moving to the casing, velocity will remain almost constant. Then what is happening? Very important, that when it is coming from penstock and moving to the casing, then since it completely surrounds, the casing completely surrounds the runner, so it will try to go to the passes in a runner passes through certain arrangement. So, water will come from penstock, it will move through the scroll casing where the velocity will remain constant. Then since the casing entirely surrounds the runner, then water will go to the runner through certain arrangement where we are having wicket gates or guide vanes. So, why you are having wicket gates or guide vane? Because each wicket gate and guide vane, I mean these are placed around the periphery of the runner. The wicket gate and guide vanes are placed around the periphery of the runner, and each of the wicket gates are pivoted. Each guide vane or wicket gate pivoted by suitable mechanism, and it is possible that at a given time we can have, since they are pivoted by suitable mechanism, either we can alter their their opening at a time. At a given time we can alter the opening of all the wicket gates, or if it is possible that we can alter the opening of a few or certain amount of a certain number of wicket gates. This is possible. So, we will discuss what is a function of wicket gates. So, before we go to discuss about this, first water will come from penstock, it will move through the scroll casing where velocity will remain constant, then water will go to the runner, and whenever it is going to the runner, it will pass through the wicket gates. Now, wicket gate or these guide vanes are pivoted by suitable mechanism. We can have, all of them can be tuned at a time to alter the direction of quantity of water. Note that this, guide vane, the function of guide vane is to direct the fluid. What is the function of guide vane? The function of the guide vane is to direct the fluid to an appropriate angle of the runner, I mean as per the designer choice. So, whenever working fluid is coming from runner from scroll casing, wicket gate will try to direct the fluid to the runner at the angle to the designer choice. So, now as I said you, all the wicket gates are pivoted by suitable mechanism, all of them can be tuned at a time essentially to alter the direction of the quantity of water depending upon the load. So, maybe from a hydroelectric power plant we will discuss, maybe if time permits, that how we can control speed governing mechanism. It is not always true that we have to have always turbine will run at the same speed, because you need to vary the depending upon the load requirement. Now, that is known as speed governing mechanism, but the wicket gates can be tuned at a time essentially to alter the quantity of water that is going to the runner depending upon the load requirement, and all the wicket gates are pivoted by suitable mechanism by virtue of which we can tune, we can alter the opening. So all of them can be tuned at a time, or if it is required that no fine, but we can operate only a few, that is also possible. This movement of the guide vane, how? Now question is how we can tune the movement of the guide vane, either all of them or a few of them, by that can be done by a speed governing mechanism of the turbine. Now question is, whenever water is entering to the runner, I mean whenever water is entering to the runner, the ends passes through the runner. Whenever fluid or working fluid is entering to the runner, during its passes through the runner blade, the fluid is deflected because of runner blades, so that its velocity of wall, that is swirl velocity, decreases. So I will write here now a few important things. So we have discussed that water will come through penstock, it will go through the scroll casing. Scroll casing is designed in such a way that velocity will remain constant. Then water will go through the guide vane and it will enter to the runner. The function of guide vane is that the guide vanes are pivoted by suitable mechanism, and the opening of the guide vane, rather the tuning of the guide vane is controlled by speed governing mechanism. We can tune all the wicket gate at a given time, or essentially to alter the direction of fluid flow depending upon the load requirement. And second thing is, whenever our working fluid is passing through the runner, there you know that I mean working fluid will be deflected, you know, because of the guide vanes, will be deflected because of the runner blades, or I mean either water or working fluid, whatever it is, in its passes through the runner, fluid will be deflected because of the runner blade, and so that the velocity of wall will decrease. This is very important. So I am writing, this is the overall situation. Now when working fluid is going to the runner from wicket gates, through the passage of wicket gates, guide vanes when working fluid is going to the runner through the passage of guide vane, in its passage fluid is deflected because of the, you know, by the runner blades, deflected runner blades, so that its velocity of runner blades, so that its velocity of swirl, velocity of wall or swirl decreases. This is important. So the velocity of swirl will decrease. So let us first now discuss about the working function of the guide vanes. So as I said you that guide vanes are placed around the periphery of the runner of the turbine. Guide vanes are pivoted by suitable mechanism, and that all of them can be tuned at a time, essentially to alter the direction of flow depending upon the requirement, and they can be tuned by speed governing mechanism. So what are the function of guide vanes? So if I write that function of guide vanes, what is the function of guide vanes? Very important, or we can get essentially partial kinetic energy conversion. Number one is not full but partial kinetic energy conversion, that is partial velocity head will be converted to the overall head will be converted to the kinetic head and velocity head. Number two, guiding the absolute velocity of fluid, guiding the absolute velocity of the fluid, working fluid, guiding the absolute velocity of the fluid, we can change the guiding angle. Number three, it acts as a governor, controlling the amount of fluid from penstock. So it acts as a governor, I mean it control. So it acts as a governor. That means by suitably tuning the guide vents we can get, we can control the direction of fluid flow, we can control the amount of fluid that is entering, so that it acts as a governor, speed governing mechanism. So we can have, depending upon the requirement of the load from that particular power plant, we can change the how much quantity of water will go to the runner at a given time by opening the wicket gates also, and it also, as I said you, that it also helps in converting the partial amount of kinetic energy. So these are the function of a wicket gates. It is a very important function. It acts as a governor, that means its control the direction of fluid flow, which can be done by speed governing mechanism, that we can tune the its opening, so that that amount of liquid as well as its direction can be controlled depending upon the load requirement. There is of course a partial kinetic energy conversion within the bucket itself, and of course guiding the absolute velocity of the fluid. As I said you, that when fluid is coming from guide vents and it is entering to the runner, in its passage fluid velocity is deflected by the runner blade, so that the velocity of the valve decreases. So I mean, it is very important that the guiding the absolute velocity of fluid, we can change the guiding angle, since its absolute velocity of the fluid is guided by this, so we can change the guiding angle. Fine. Another important part of that particular turbine is that we are having draft tube. What is the function of draft tube? So when water is coming from runner, I mean, of course from the center of the runner, all the fluid turn into the axial direction of the and flows to the tail race level through the draft tube. So from the center of the runner, so when water is coming from the center of the runner, fluid is turned into the axial direction, so I am writing from the center of the runner. So what is the function of draft tube? Very important. This is another important part of this turbine. So what is the function of draft tube? Let me discuss about that. Draft tube shape is that it is gradually increasing in its cross section area. So whenever water is moving through the draft tube, we can have a recovery of the some amount of kinetic energy to the equivalent amount of pressure head, because maybe all the overall head is not converted in the turbine itself, there will be some amount of kinetic energy. So to gain that amount of kinetic energy, instead of wasting this kinetic energy, we can have a certain arrangement so that we can recover. So this is very important. So what is the function of draft tube? So when rather from the center of the center of the runner, fluid is turned into the axial direction, into the axial direction, and flows to the tail race, through the draft tube, flows to the tail race through a passage which is called draft tube. So from the center of the runner, fluid is turned into the axial direction and flows to the tail race level, and whenever it is flows to the tail race level, then it flows through flows to the tail race level. When it is going to the tail race level, it flows through a particular shape of passage which is known as draft tube. So and the lower end of the draft tube must under all condition operational be submerged at tail race level. This is very important, that the lower end of the draft tube at all working condition, must be submerged below the tailwater level, must be submerged below the tailwater, below the water level below the water in the tail race, below the water of tail race. So, this is very important that what is the function of draft tube, that is very important. This is special arrangement, that lower end of the draft tube at all working condition must be submerged below the water of a tail race level. Since, and as I said you, the cross section of the draft is gradually increasing in the direction of flow to minimize the kinetic energy loss at the turbine. So, since the lower end of the draft tube at all working condition must be submerged below the water race level, it helps to install the turbine at an elevation higher than that of the tail race without losing it any effective head. So, because of this, it helps to install the turbine at an elevation higher than the TRL, at an elevation higher than the tail race level, higher than the TRL, so that higher than that of the TRL. It helps to install the turbine. It helps to install the turbine at an elevation higher than that of the TRL, tail race level, without sacrificing any working head, without sacrificing any effective head. That means, without sacrificing effective head, we can install turbine at a elevation which is higher than the TRL, because that is only possible because of the draft tube. So, the draft tube, what is the function? From the center of the tunnel, fluid is turned into the axial direction and flows to the TRL level through a passage which is known as draft tube. The lower end of the draft tube at all working condition must be submerged in the tail race level, and since we are having draft tube, so it is always possible that we can install turbine at a elevation which is higher than the water level in the TRL without sacrificing any effective head. Now, the draft tube, as I said you, its cross sectional area gradually increasing in the direction of flow, so that, as I said you, that maybe all the overall head is not converted into the kinetic head. So, some remaining amount of pressure head is still there. So, you can convert that into the gradually increasing area, so reducing the velocity. So, to minimize, so maybe all the the head converted to the pressure head into the kinetic head, maybe it is not used to obtain equivalent amount of power. So, whatever amount of kinetic head you are having at the end of the turbine, you can regain that kinetic energy into the equivalent amount of pressure head. I do not know whether the equivalent amount of pressure head or not, but still some unutilized kinetic energy can be again recovered whenever fluid is flowing through the draft tube because of its shape. So, the cross section area is gradually increasing, that means in the direction of flow, so that unutilized or the remaining kinetic energy can be converted to the pressure head, whether by an equivalent amount or not, that is very difficult to say, but still that so that the remaining kinetic energy can be converted, converted to the pressure head. That means kinetic energy loss can be minimized. So, this is all about the reaction turbine, that how we can have a different. So, we have discussed different parts, operational principle of a reaction turbine, how it is differing from the impulse turbine, and there are a few parts which are integral to this turbine, and we have discussed about their function. Draft tube is very most important part. Because of the draft tube, we can install turbine at a elevation level which is higher than that water level of the TRL. Not only that, draft tube helps in recovering the remaining kinetic energy to the pressure head, so that the efficiency can be increased. Not only that, the kinetic head loss can be minimized. So with this background, we now next to move to solve one problem on this reaction turbine. So we will solve one problem on reaction turbine, and we will write the problem first. Problem on reaction turbine. In a vertical shaft inward flow reaction turbine. So in a vertical shaft inward flow reaction turbine, the vertical flow reaction turbine, sum of the pressure and kinetic heads at the entrance to the spiral casing is 120 meter. Sum of the pressure and kinetic head, pressure and kinetic heads at the entrance or at the inlet to the spiral casing, at the inlet to the spiral casing is 120 meter, and the vertical distance between this section and tailor L, and vertical distance between this section and TRL, tail raise level, is 3 meter, right. Peripheral velocity of runner at entry, the peripheral velocity of runner at entry, peripheral velocity of runner at entry is 30 meter per second. The radial velocity of water is constant, and that is 9 meter per second. Discharge from the runner without discharge from the runner is without swirl, and discharge from runner is without swirl. Fine. The estimated Hartley losses are, so estimated hydraulic losses are very important between turbine entrance and exit from the guide vanes. 1, between turbine entrance and exit from guide vane is 4.8 meter. Number 2, this is 4.8 meter. Number 2, the runner, in the runner it is 8.8 meter hydraulic losses. Number 3, in the draft tube 790 meter, in the draft tube, because frictional hydraulic losses we cannot ignore, in the draft tube it is 790 millimeter. Number 4, very important, kinetic head rejected to tail raise. Still, even though we are having draft tube, but still some amount of kinetic head is remaining, we cannot recover all this. That is why I told that whether I do not know, we can convert equivalent amount of pressure head or not, that is not possible at all. So kinetic head rejected to TRL is 460 millimeter. 460 millimeter. This is 790 millimeter. So we have to calculate, very important, guide vane angle at the runner and the runner blade angle at the inlet. So we have to calculate, this is very important, guide vane angle and runner blade angle at inlet and pressure head at entry and entry to and exit from the runner. 1, 2 pressure heads at entry through and exit from the runner. Okay, so we have, this is the problem, we have to solve this problem. So this is the problem, but we need to solve. How can we solve that? We need to solve again. We will solve it. It is not very difficult problem at all because we know everything. So how we can solve? This is very important because so it is given that in a vertical shaft inward flow reaction turbine, sum of the pressure and kinetic heads at the inlet of the spiral casing 120 meter, and the vertical distance between section TRL and TRL between this section and TRL is 3 meter. Peripheral velocity of runner at the entry is 30 meter per second. Radial velocity of water is constant 9 meter per second. Discharge from runner is without swirl. We have to calculate hydraulic losses is given between turbine entrance and exit from the guide vanes. Runner it is given. Draft it is given. Kinetic energy rejected to TR is given. So we have to calculate guide vane angle, runner blade angle at the inlet, pressure head at entry and to exit from the runner. So we have to solve this problem. So we now will solve solution. Very important. So if I draw the schematic, suppose this is the so this is head rest level, it is coming from penstock, and this is turbine. So we are having, let us say this is the turbine. So we are having draft tube, so from where water is discharging, and this, as I said, the draft tube will be always submerged below the TRL. So this is TRL, this is TRL, and so this is, let us say this point is A and this point is B and this is A. So this distance is ZA. Right. So if you draw the velocity triangles, how we can obtain velocity triangles? We can obtain inlet velocity triangles. So this is U1, this is W1, and this will be C1. W1, this angle is beta 1, this angle is alpha 1, this is U1, this is C1. So now this is outlet velocity angle W2, there is no swirl, it is given. So this is C2, this is beta 2, this is W2, and this is U2. It is given that no swirl. So if I go back to my previous slide, it is given that it discharged from runner without swirl. So it is 90 degree. So how we can solve this problem? So total hydraulic losses is equal to how much? It is given 4.8 plus 8.8 plus 0.79 plus 0.46 meter, that is equal to 14.85 meter. This is total losses. Now it is given that PA by rho g plus VA square by 2g is equal to 120 meter. That is what is very important. At the sum of the pressure and kinetic at the inlet to the spiral casing. So A is the inlet to the spiral casing. The point A is the inlet to the spiral casing. So this is given 120 meter. ZA, that is equal to 3 meter, that is given. The distance between this section inlet to the spiral casing and TRL is 3 meter. So this is 3 meter is given, right. U1 is equal to 30 meter per second the peripheral velocity of the runner at inlet. So, this is peripheral velocity at runner inlet, this is given, and if I call it is let us say CR1 and CR2 is equal to C2. So, CR1 is equal to CR2 is equal to C2 is equal to 9 meter per second, it is given, that is radial velocity of water, radial velocity of water, that is also given. So, what we have to calculate? We have to calculate the beta 1 and beta 2 that we have given. So, we need to calculate something that already we know that we have to calculate guide vane angle, runner bed angle at the inlet, pressure heads at entry and exit from the runner. So, we will proceed to solve again. So, we know this data, then you know this 120 plus 3, this 120 plus 3, that is total head, that will equal to how much? 14.85, that is losses, plus u1 c theta 1 by g, plus u1 c theta 1 by g, that is the equation. Therefore, from here we can obtain u1 c theta 1 by c theta 2 is equal to 0, since c theta 2 is equal to 0. So, that will be equal to how much? 108.15. So, I know u1, from there we can obtain c theta 1, c theta 1 will be equal to 35.37 meter per second, right, because so we have obtained the swirl velocity at the inlet 37 per second. So, from the inlet velocity triangle, again if I draw the inlet velocity triangle, so this is u1, this is w1, so this is c1, this is w1, and this angle is beta 1, this is alpha 1, right. So, how I can obtain and this is 9 meter per second, that is CR1, CR1 is equal to 9 meter per second, it is given. So, alpha, that is we need to calculate, that is tan inverse how much? 9 by 35.37, because c theta 1 was how much? This will be c theta 1. So, alpha will be equal to how much? 35.37 is equal to that is what you have obtained c theta 1. So, this is 35.37, right, that is equal to 14.28 degree. Similarly, beta is equal to tan inverse 9 divided by how much? That is this entire is c theta 1. So, this is c theta 1. So, c theta 1 minus w theta 1, this is quantity that is equal to let us say L. So, tan inverse 9 by L, and what will be L? Because I know u1 is equal to how much? u1 is equal to given, speed is equal to given. If I go back to my previous slide, speed is given 30 meter. So, so it should be 35.37 minus 30. So, this will be 35.37 minus 30, that is tan inverse 9 by 5.37, and that is coming around 59.2 degree. So, these two are obtained. Now, V1 square by C1 square by 2g, C1 square by 2g equal to 35.37 square plus 9 square divided by 19.62 2g, and that is equal to C1 is equal to how much? Because CR1 square plus C theta 1 square. So, this is equal to C1 square plus C theta 1 square. So, that will be coming equal to 67.9 meter. So, now 120 plus 3, that will be equal to 4.8 plus P1 by rho g plus C1 square by 2g plus 3. From there I can calculate P1 by rho g will be equal to 115.2 minus 67.9 meter, that equal to 47.3 meter. This is P1 by rho g. Now, what will be P2 by rho g? That is what we need to calculate, because that is very important. That is because pressure head at the entry and exit to the runner. So, entry to the runner is P1 by rho g. So, P1 by rho g plus C1 square by 2g plus 3 plus 4.8, that equal to total head 120 plus 3. Apply Bernoulli equation between, so this is obtain, apply Bernoulli equation between A and B. B is entry to the runner, right. So, we can obtain from there. Similarly, I can obtain P2. So, P2 by rho g, that is the exit from the runner, plus C2 square by 2g plus 3 is equal to 0.46 plus 0.79 meter total losses. So, from there I can calculate P2 by rho g. It again we have to apply Bernoulli equation, right. We have to apply Bernoulli equation between section entry and the that 0.46 and 0.49, that these are given, no, 0.46 and 0.49 are given, draft tube and the current rejected TRL. So, these two are given. So, if I apply P2 by rho g plus C2 square by 2g plus 3, taking that is a datum, then 0.46 plus 1.79. So, it will be coming around 0.46 plus 0.79 minus 3 minus C2 square is equal to 19.62, that equal to minus 5.88 meter. Since C2 is equal to CR2 is equal to CR1 is equal to 9 meter per second. So, we have obtained everything. So, we have obtained that pressure which is available, that is what, that angle pressure head at the entry and exit from the runner, entry of the runner at the point B, So, this is pressure at the entry to the runner, that is at point B. Similarly, at exit of the runner, that is P2, exit of the runner is this point, let us say C, and that is pressure at the exit from the runner. So, we have obtained all the answer. So, we have to solve the problem in this way. So, with this I stop here today and we will continue our discussion in the next class. Thank you.